Hello. In this video, we're going to be studying another topic in math called matrices. Now, of course, The Matrix is a fantastic film starring Keanu Reeves, Lawrence Fishburne. It's a wonderful movie. You should take a look at it if you've never seen it. Excellent piece of film. But we're going to be studying the mathematical topic of matrices. And so, let's start with matrix operations. Now, for a motivation, a question you might ask is, how do computers know how to read numbers? If you think about it, you can sometimes take your phone and you can scan things. You might have seen something like PhotoMath. PhotoMath. It's definitely an app worth checking out as a math student. You can point your phone at a piece of math and it'll often do the math for you. It's very cool. But the question is, how does it do that? How does your phone know how to do math? Well, maybe you could say the phone has a calculator and it has access to Desmos or the internet, and the internet can do calculations. Sure, but how does your phone know how to read the numbers? How does it convert the picture into actual text, into actual code, into actual numbers that it can use? And it's what is called is optical character recognition, OCR, and it uses a matrix. So what is a matrix? Well, a matrix is a big box of numbers. For example, 1, 3, 4, 5. This is a small box, but the box could be very big, something like this. It's a giant box, and it's got the numbers 14, 32, 1, 2, and so on. And this box, the whole thing, is called a matrix. The matrix is just the box that holds all these numbers. And you could have all sorts of numbers. You could have negative numbers, you could have decimals, you could have fractions. It doesn't matter what's in the box, it's just that we have numbers in the box. Now, we need to start to talk about these matrices and give them some terminology. For example, does anyone know what we would call a line of numbers that goes across? What would you call something like this? If you had a line of numbers that goes across, any idea what word you would use? Well, you would use the word row. If you have a line of numbers across, that would be called a row. What do you think a line of numbers that goes down? Well, thinking about Excel or a spreadsheet, that would be a column. And so what we have is we have a matrix that has, of course, a row. In this case, we have 2 rows. And we have matrices that have columns. In this case, this one has 3 columns. And we could talk about these rows and columns, and they would be called the dimensions of the matrix. So this matrix up here is really big, this one's a bit smaller, and the dimensions of a matrix describe its size. In particular, we write the number of rows and the number of columns. So the number of rows and the number of columns together give us the dimensions of a matrix. So let's look at some examples here. What do we think the dimensions of this matrix are? Well, we have 1, 2, 3 rows and 1, 2 columns. So we have 3 rows, 2 columns. So it would be a 3 by 2 matrix. That's how we say it. It's a 3 by 2. All right, the next one down here. Give it a try for D. What do you think this matrix would be? All right, we've got 4 rows and 3 columns, so this is a 4 by 3 matrix. Now, how about F? F is a little tricky. There are 3 rows, but only 1 column. So this is a 3 by 1 matrix. All right, so we can label the size of a matrix. What's the next thing we'd want to do? Well, in math, the first operation you learn how to do, of course, is addition. And matrix addition is calculated in the very natural way. If you looked at these 2 matrices, these 2 boxes of numbers, and you wanted to add them, hopefully your intuition would say, well, I'm going to add them up something like this. I'll make another box over here. And I'm going to say 1 and 5. I'm going to add those up to give me 6. 3 and 2, I'm going to add those up to give me 5. 4 and 1 also add up to 5. And 7 and 6 add up to 13. So what we've done here is we've calculated addition by adding corresponding entries. which is really the only way to add it. It wouldn't make sense to add it any other way. We look at the 1 and the 5 and we add those up, the 3 and the 2, and so on and so forth. So pause the video and try these next two examples for adding matrices. Alright, so assuming you gave it a go, let's look at this first one here. 4 and 1 will be 5. Negative 2 and 7 will also be 5. 3 and 6 will be 9. And 11 and 14 will be 25. Now this bigger matrix over here, we have to make a little more space when we do this. We're going to get 3, 6, 9, 5, 8, 11, 17, 16, 15. So some good practice with addition there. Now what about this situation here? 3, 5, 1, 7 plus 1, 5, 13, 4, 1, 6, 7, 0, 8. Well, we try to add the 3 and the 1 and the 5 and the 5, but what do we add to the 13? It seems like this whole column over here is going to have nothing to add with. And if you notice, back on these matrices, this, for example, is a 3 by 3. And this is also a 3 by 3 matrix. And it gave you, in the end, a 3 by 3. But over here, this is a 2 by 2. And this is a 3 by 3. And if you try to add a 2 by 2 matrix to a 3 by 3 matrix, it is impossible. It is impossible because the matrices here are of different sizes. And you can't add two matrices of different sizes, of different dimensions. It doesn't make sense. It doesn't compute. So as a remark, if matrices have different dimensions, then we cannot add them. All right. Let's try a bit of a working backwards example here. Let's determine the missing entries in the following matrix equation. So we have these two matrices should add to this matrix, but we have a few missing entries. So pause the video and give it a try yourself. All right, well, it looks like this should be a 2 here because 3 plus 2 should give us 5. Now 1 plus 4, that's obviously 5 as well. Over here, 4 and 11 will be 15. And working backwards here, something plus 3 gives 0. That will be negative 3. All right. Now, how about multiplying? Because after addition, of course, the next thing we learn after subtraction would be multiplication. Well, the thing about matrices is there's actually two different ways to multiply. The first way is if you have a number in front and you're multiplying the matrix. This one, again, I think is pretty intuitive. If you have 4 times this matrix, it's kind of like distributing. The 4 goes to the 2 and the 1 and the 7 and the 5. Each one of them gets multiplied by 4. So you get 4 times 2 is 8, 4 times 1 is 4, 4 times 7 is 28, 4 times 5 is 20. Each part gets multiplied by 4. And you can do the same thing with different numbers. A 3, a 2, a 0. We're going to call this here type 1 multiplication. It's where you have a number times a matrix. So let's rattle these off pretty quick. This will be 6, 3, 21, and 15. This will be 8, 2, 14, and 22. Well, this will be 0, 0, 0, 0 because 0 times anything is just 0. Now, what about multiplying two matrices? Well, this is a little bit tricky, a little bit more involved. If we have two matrices here and we need to multiply them, you might think we do 2 times negative 1 and then negative 2 times 4 and 5 times 7 and 3 times negative 6, where you multiply corresponding entries. And this is actually a type of multiplication, but it's not the type of multiplication we're going to be looking at. It is a type of multiplication. You can do it in computer science. And it's a type of matrix multiplication, but it's not the type we're interested in. In fact, the type we're interested in is a little bit more complicated, but also a little bit more interesting. So I encourage you right now to pause the video and take a look at this example. The link for this video is in the description. So this is a nice example of multiplying matrices. And so please pause the video, take a look at this video, and then we're going to pop back to the original one here. So assuming that you have taken a look at the video, we're going to redo the example just to make sure everyone's on the same page. So to start, I'm going to just rewrite these a little bit different to help us visualize what's happening. So we'll take the first matrix over here, and then I'm going to stack the second matrix up top. Alright, and so when we go to multiply, we're going to be filling in this matrix here. And what happens when you multiply matrices is you take the first row of the first matrix and the first column of the second matrix, and you kind of smush them together. It's as though these two, let's do this in another color. It's as though this row and this column get smushed together. And the way they do is you do 2 times -1, which is -2. And then you do -2 times 7, which is -14. So next, let's smush this row with this column. So 2 times 4 will give you 8. -2 times -6 will give you 12. All right, let's smush this row with this column. So we'll get -5 plus 21. And finally, let's go ahead and smush this row with this column. That'll give us 20 minus 18. And so then you go ahead and do the addition to simplify it. So this gives us -16, 20, -16, and 2. So it's not obtained by doing 2 times -1, which would give -2. That does not give us the correct answer. It's this combination of multiplying the columns, or the rows, sorry, of the first matrix by the columns of the second matrix. So let's practice some examples to get proficient with this. So we have some matrices here, and again, I encourage you to pause the video and give these a try, and then I'll go ahead and multiply them. All right, so the first one here, 1 times 2. So we're taking this row and this column. So 1 times 2, that's going to be 2. 3 times 7 is 21. That gives us the first entry. Then 1 times 3 is 3. 3 times 0 is 0. 2 times 3 is 6. 4 times 7 is 28. 3 times 3 is 9. 4 times 0 is 0. And we clean up the addition to give us 23, 3, 34, and 9. Now, if you want, you're welcome to try these in just one go if you can do all the addition in your head. So 2 times 7 will be 14. 1 times 1 will be 1, which is a total of 15. 2 times 1 is 2, and 1 times 5 is 5. So we have 5 and 2 is 7. This is going to be 70 and 6, which gives us 76. This is going to be 10 and 30, which gives us 40. All right, now I'll go ahead and write out the next one for you. 3 times 4 plus 2 times 1. 3 times 8 plus 2 times 9. 0 times 4 plus 1 times 1. And then 0 times 8 plus 1 times 9. So cleaning all that up, we're going to get 12 and 2, which is 14. 24 and 18, which is 42. 1 and 9. All right. Now, we can actually multiply matrices that are of different sizes, and this is what's very interesting. If you go to start doing this, well, you'll go 3 times 6 plus 4 times 4. And then you go, okay, well, there's no other column, so we'll go down to the next row. 7 times 6 plus 2 times 4, which gives us 18 plus 16, 42 plus 8, and so our final answer is 34 and 50. Now if you notice here, this is a 2 by 2, and this is a 2 by 1. So the way it has to work for matrices is these two need to match. There are some specific conditions where you can't multiply. If these ones don't match, then you won't be able to multiply. But as long as they do, they'll match, and these two will give you your result. If you notice, our final answer over here is indeed a 2 by 1 matrix, and that's because 2 by 1 gives us our resulting dimensions. So try the next one, see what you get. All right, you should get 44 plus 3, and then 110 plus 36, so 47, 146. All right, now try these two questions and see what you notice about this matrix multiplication. Well, if you do the multiplication, you should get 7, 3, 5, and 4. And over here you should get 5 and 8, and 9 and 0. And if you notice, it's kind of weird. This and this, they're the same. Same thing here, this and this, same. So, same. Which is kind of strange that you could multiply by a matrix and it wouldn't change. Well, let's talk about this a little bit more. What special number can you always multiply by to leave the other number unchanged? Thinking about regular arithmetic. Well, hopefully you remember the special number is the number 1. Because 1 times anything is just the anything. Well, what special matrix can you always multiply by to leave the other matrix unchanged? Turns out that 1, 0, 0, 1, if we multiply this, we'll give a plus 0, 0 plus b, c plus 0, 0 plus d. So it wasn't actually a fluke with that question. We're always going to get the same thing. It's going to be unchanged. And so this matrix right here, this is a very special matrix, and it is called the identity. The identity matrix. Just like the number 1 is an identity number, when you multiply, it gives you identically back what you started with. This number, or this matrix, I should say, it does the same thing as 1. It multiplies the matrix and doesn't change it. Which is an interesting fact about matrices. In some ways, matrices act like numbers. They have some similar properties. Numbers have a special number that doesn't change when you multiply, and matrices have a special number that doesn't change when you multiply. But matrices are not exactly the same as numbers, because even though you can multiply and add matrices just like you can multiply and add numbers, there's a special property of numbers that's not true about matrices. In regular numbers, we know that 3 times 5 is equal to 5 times 3 because both ways gives 15. But is the same true for matrices? Is a times b equal to b times a? Well, let's go ahead and give it a try. So a times b would be equal to 2, 4, 1, 5 times 7, 3, 1, 6. That's going to give us, well, 2 times 7 will be 14, plus 4 is 18. 2 times 3 is 6, plus 24 will be 30. 7 times 1 and then 5 times 1, that'll be 12. And then 33. So A times B gives this. What does B times A give? Well, 7, 3, 1, 6 times 2, 4, 1, 5. 7 times 2 will be 14, plus 3 will be, 17. And then 7 times 4 plus 5 times 3, well, that's going to be 43. 2 times 1 and 6 times 1, that's going to give us 8. And then 4 times 1 and 6 times 5, that's going to give us 34. So notice, these two final results are different. So does it give us the same? The answer is no, it does not. So A times B is not equal to B times A. You can't just multiply it in either order. Now you've actually seen this in mathematics before. You might not remember, but in pre-calculus, f of g of x was not equal to g of f of x. You couldn't just do the function composition in either order. And so you have seen this property before in mathematics. As a nice example, let's think about what's called sometimes shoes and socks. So if you're getting ready in the morning and you put on your socks, and then you put on your shoes, well, you're a regular person. You've gotten ready for the day, you're good to go, you got your socks on, and then your shoes. But what if instead you decide to switch the order because you thought in math, oh, I can do things tomato, tomato, either way it doesn't matter. I put on my shoes first, and then I put on my socks. Well, you're going to look a little bit ridiculous if you put on your shoes first and then your socks, because now you've got these socks over top of your shoes, and people are going to think you're weird, and you don't look like you're ready for the day, because socks then shoes is not equal to shoes then socks. They don't go in either order, and just like shoes and socks would be a little bit weird instead of socks and shoes, the same thing is true for matrices. You can't switch the order and expect to get the same answer. Now let's look at another interesting thing that's different about matrices compared to regular numbers. Can you find two non-zero numbers that multiply to give 0? Like 3 times negative 2, is that going to give 0? Or maybe like a half times 5? Well, I don't think so. If you have A times B equaling 0, I think one of them has to be 0. I don't think there's any way you could make those both non-zero and get 0. So this is no. There's no way you could do that. But look at this in matrix land. Here's a non-zero matrix because it's not all zeros, and here's another non-zero matrix. So let's multiply this. 1 and then negative 1, that'll be 0. I'll write this out just to see. So 1, subtract 1. And then 1, subtract 1. 1, subtract 1. 1, subtract 1. Oh, look. We get all zeros, also called the zero matrix. And so this is very strange. You can have two non-zero matrices that multiply to give a completely zero matrix. And so the takeaway here from this is that the matrix world is very different from the real number world. That's not to say either one is better or worse, but you need to be careful when doing work with matrices because some of the properties are similar, but some of them are very different. And you don't want to assume something incorrectly in the matrix world because it can lead you astray. Now let's look at a practical example of matrices. Suppose you score 75% on the tests in class and 90% on the assignments. What is your final grade using the following weighting? We have tests and assignments. Tests are 60% and assignments are 40%. Well, hopefully you can do some basic weighting arithmetic here. It's a little tricky, but what we do is we take the 75% that you scored on the tests and we multiply it by 0.6 because that's how much the tests are worth. Plus, we do 90% that you got on the assignments times 0.4 because that's how much the assignments are worth. And you can use a calculator for this. You'll get 81%. So there's your final mark, 81%. All right. Well, let's suppose your friend has the following scores. And then can you calculate their final mark? Maybe they got lower on the test. They got only 60% and they got 85% on the assignments. Well, sure, you can help them out. You can grab a 60%, times it by 0.6, and an 85%, times it by 0.4. And again, with a calculator, you can work that out. That would be 70%. But what if you were a teacher and you had to calculate everyone's final grade? I mean, this is kind of my situation. I don't have just 1 or 2 final grades I have to calculate. I have to calculate it for all the students. Is there a way to maybe use a matrix? Well, just for fun, let's multiply this matrix by this other matrix. So again, you're welcome to use a calculator. 75 times 0.6 plus 90 times 0.4. Well, that's going to give 81. And 60 times 0.6 plus 85 times 0.4, that'll give you 70. Hey, wait a minute, what do you notice about this answer? Well, this answer right here is the 81%. And this 70 is the 70%. It's the same as before. And if you notice, the matrices here I picked were not random. The 75 and the 90, this row, was your marks. And the 60 and the 85, it represented your friend's marks. This matrix over here, it represented the weighting, the 60% for the tests and the 40% for the assignments. All right, so let's try to set up our own example. Let's suppose Arsh got 70% on the tests and 90% on the assignments. Colleen got 80% on the tests and 70% on the assignments. What are their final marks? Let's see if we can build the matrix. Well, Arsh got 70 and 90, so 70 and 90. And then Colleen got 80 and 70. And the weight is still 0.6 and 0.4. Well, if you go ahead and grab a calculator and multiply 70 times 0.6 plus 90 times 0.4, you'll get 78. And then 76. So what are their final marks? Arsh got 78%. And Colleen got 76%. So you can figure out their marks directly using a matrix. Now let's suppose the teacher changed the weighting. Let's suppose the teacher said, you know what, those assignments were too easy, everyone was doing too good on those. I'm going to make the test worth 80% and the assignments worth 20. Could we figure out their final marks now? Well, of course. The first matrix will stay the same, 70 and 90. And then the next part will be 80 and 70. But the second matrix changes. It becomes 0.8 and 0.2. So I'll give you a second to work that out on a calculator. So you should be getting 74 and 78, which is kind of weird. If you notice, they didn't do any better or worse in the class, but the teacher changed the weighting. And suddenly Arsh went down 4% and Colleen went up 2%. Over here, Arsh might have been feeling pretty good. He beat his friend Colleen. He had the higher mark. But over here, Colleen beat Arsh, and now Colleen has the higher mark. What do you think about these new marks? Does this feel fair? Well, I mean, I guess if you're Colleen, you're pretty happy. But does it feel right that the teacher can change their final marks just by tweaking the weightings over here? Hopefully you feel like this is a little bit unfair, a little bit unjust. And in fact, in university courses, the weighting is set out at the beginning of the course, and it can't be changed. The weighting is agreed to at the beginning of the course, it's in your course outline, and it can't be changed randomly throughout the course to avoid something like this, because it's kind of unfair to hand in all your work only to have your final grade changed just because the teacher wants to change some kind of weighting. So hopefully in high school you were also given course outlines that indicate the weighting, because you don't want to have these things changed on you last minute. Just feels a little bit insincere. Now, for some examples, please try these matrix operation questions. When you do the subtraction, it's the same as addition, but you just subtract the matrix entries. And of course, make sure that when you're subtracting a negative, you get a positive. So the answers are in the back, and if you have questions, feel free to send me a message. And as always, thanks for watching.